As we can see, if f is a function from Rn to the extended real line, with non-empty domain, then its Fenchel conjugate is given by this formula. The supremum of the inner product of v and x minus f of x, where x runs in Rn. Then f star is a function from Rn to the extended real line. So, because it's a function from Rn to the extended real line, we can define the Fenchel conjugate of f star. So then we define f double star of x to be f star star of x. Okay? So, by the definition, the Fenchel conjugate of f star of x is equal to the supremum of the inner product of x and v minus f star of v, where v runs in Rn. Okay? And therefore, we obtain the following formula for computing the second order Fenchel conjugate of the function f at x. This is just the supremum of xv minus f star v, where v runs in Rn. And with this definition, we see that f double star is a function from Rn to the extended real line. And over here, minus infinity is included. Okay, and again, if we can impose some condition to make sure that the domain of the function f star here is non-empty, then f double star is an extended real value convex function. Okay, so in the next proposition, we are going to learn the relation between the second order Fenchel conjugate of f and the function f. Let f from Rn to the extended real line be a function with non-empty domain. Then f double star of x is always less than or equal to f of x for all x in Rn. So the proof of this proposition is also simple. It's based on the generalized Young inequality established in the previous proposition. Okay, so if we fix any x and v in Rn, then the generalized Young inequality gives the inner product of v and x is less than or equal to f of x plus f star of v. Okay, and from here we have that the inner product of v and x minus f star v is always less than or equal to f of x. Okay, note that this is true for all v in Rn. So if we take the supremum of the left hand side with respect to v in Rn, the inequality remains true. So we continue the proof by having this. It follows that the supremum of the inner product of V and X minus F star V, where V runs in Rn, is still less than or equal to f of x. And therefore, f double star of x is less than or equal to f of x. And the proof is complete. Note that the left hand side here is nothing but f double star of x. From the generalized Young's inequality, we see that the inner product of V and X is always less than or equal to f of x plus f star of V. This is true for all x and V in Rn. In the next proposition, we study a sufficient condition that guarantees the equality in this inequality. So this is the proposition which gives that condition. Okay, so let f from Rn to the extended real line be a convex function and that x bar in the domain of the function f. Then V belongs to the subdifferential of the function f at x bar if and only if the inner product of V and x is equal to, V and x bar actually, is equal to f of x bar plus f star of V. Okay? So in the formulation of the generalized Young's inequality, we do not require the convexity of the function f. Okay? Now, under the condition that f is a convex function and V belongs to the subdifferential of f at x bar, we actually have the equality in the Young's inequality. Now, let me go through the proof of the proposition. So, at first, we are going to show that if V is in the subdifferential of f at x bar, then the equality here is satisfied. Okay? So, this is the first implication. Let V be in the subdifferential of f at x bar. By the definition, the inner product of V and x minus x bar is less than or equal to f of x minus f of x bar, and this is true for all x in Rn. So we can rewrite this inequality as the inner product of V and x minus the inner product of V and x bar is less than or equal to f of x minus f of x bar for all x in Rn. Equivalently, we have this, the inner product of V and x minus f of x plus f of x bar is less than or equal to the inner product of V and x bar. This is true for all x in Rn. Okay? Because this is true for all x in Rn, we can take the supremum of this expression with respect to x, and the inequality remains true. So, the supremum of the inner product of V and x minus f of x, where x runs in Rn, plus f of x bar is less than or equal to the inner product of v and x bar. Now, if we remember the definition of the Fenchel conjugate, this is just f star of v. And here, this is f of x bar, and the sum is less than or equal to the inner product of v and x bar. And by the generalized Young's inequality, the opposite inequality here is always satisfied. Therefore, we actually have this inequality, the Fenchel conjugate of v plus f of x bar is equal to the inner product of v and x bar. And we have completed the proof of this implication. To prove the opposite implication in this proposition, we will assume that this inequality is satisfied and show that v belongs to the subdifferential of the function f at x bar. Okay, so suppose that the inner product of v and x bar is equal to f of x bar plus f star v. Okay, then we see that the inner product of v and x bar is equal to f of x bar plus the supremum of the inner product of v and x minus f of x, where x runs in Rn, because this is just the Fenchel conjugate of v. Okay, so then this is true. F of x bar plus the supremum of the inner product of v and x minus f of x, where x runs in Rn, is always greater than or equal to f of x bar plus v, the inner product of v and x minus f of x. And this is true for all x in Rn. Okay? By rearranging this inequality, we have the inner product of v and x minus x bar is less than or equal to f of x minus f of x bar. And this is true for all x in Rn. By the definition, v belongs to the subdifferential of f at x bar, and the proof is complete. We know earlier that the double Fenchel conjugate of the function f at x is always less than or equal to f of x for all x in Rn. In the remaining parts of the lecture, we are going to study conditions that guarantee the equality here. Okay? And at the end of the lecture, we will show that if f is lower semi-continuous and convex, then f double star of x is equal to f of x for all x in Rn. And therefore, we can establish a one-to-one correspondence from the set of all lower semi-continuous convex function on Rn to itself by this formula. So this one-to-one correspondence is very important because if we have a function f, then we can associate with f its Fenchel conjugate. And therefore, with the information from the Fenchel conjugate, we can know more about the function f. In particular, if we would like to minimize the function f, we can formulate a dual problem based on the Fenchel conjugate of f, and then sometimes solving the dual problem is easier than the primal problem, and therefore we are able to know the information about the dual problem by solving the dual problem. Okay, so in the rest of the lecture again, we are going to study the equality in this inequality. We know earlier that the second order Fenchel conjugate is always less than the function f. Okay, and in the next proposition, we will study a condition that guarantees the equality in here. So the proposition is as follows. Let f from Rn to the extended real line be a convex function and let x bar be a point in the domain of the function f. Okay. Suppose that the subdifferential of f at x bar is non-empty, then we actually have the equality here. That is, f double star of x bar is equal to f of x bar. Okay, so in particular, if x bar belongs to the interior of the domain of the function f, then the subdifferential of f at x bar is non-empty, as we saw from the previous lecture, and then f double star of x bar is equal to f of x bar. Okay. Now, if as an important case, if f is a convex function from Rn to the real line, okay, so this is a real value function, then the if we take any x bar in Rn, it always belongs to the interior of the domain of the function f, that is the whole space Rn. So in this case, we always have that f double star of x bar is equal to f of x bar, and this is true for any x bar in Rn. Okay. Okay, so the proof of this proposition is very simple. Let me go through it right here. As we know earlier, the second order Fenchel conjugate of x is always less than or equal to f of x for all x in Rn. Now we are going to study a necessary and sufficient condition that guarantee the equality in this inequality. And in order to achieve the goal, we need an important lemma that is of independent interest. If we have a convex function, intuitively we can find an R5 function that is always less than or equal to the function f. Okay, so now we will formalize this result in the following lemma. Let f from Rn to the extended real line be a convex function such that the epigraph of f is non-empty and close. there exists A in Rn and B in R such that the inner product of A and X plus B is less than or equal to f of x for all x in Rn. Okay, so if we define this by phi of x, we see that phi is an R-phi function and phi of x is always less than or equal to f of x for all x in Rn. In this lemma, we require the convexity of the epigraph of the function. We also require that the epigraph here is closed. Okay, and later on we will see that the fact that the epigraph of f is closed is equivalent to the fact that f is lower semi-continuous. Okay, and we also need one condition, one additional condition, that is the epigraph of f is non-empty. This is always satisfied, for example, when the domain of the function is non-empty. Okay, so geometrically, the proof should be based on convex separation theorem. So let me go through the details of the proof. So from the assumption, as we see earlier, the epigraph of the function f is non-empty, closed, and convex. Okay, and therefore we can fix an element x naught that is in the domain of the function f, and this is f of x naught. So the idea of the proof is very simple. We are going to fix a number lambda that is lambda naught that is strictly less than f of x naught, so that the point x naught lambda naught is not in the epigraph of the function f. And then by the convex separation theorem, we can use a hyperplane in order to separate the epigraph of f and this point strictly. And from this hyperplane, we can define the R-phi function that satisfies the required property. Okay. However, we will prove it formally as follows: fix x naught that is in the domain of the function f. This is okay because the epigraph of the function is non-empty, and therefore the domain of the function has to be non-empty. And then fix lambda naught in R such that lambda naught is strictly less than f of x naught. So the point x naught lambda naught is not in the epigraph of the function f, which is a non-empty closed convex set in Rn plus 1. Okay. Next, we are going to apply the convex separation theorem on Rn plus 1 by the strict separation theorem. There exists an element denoted by V gamma that is non-zero and epsilon greater than 0, such that the inner product of V and X plus gamma times lambda is strictly less than the, it is fine to write less than or equal to the inner product of V and X naught plus gamma times lambda naught minus epsilon. Okay, and this is true for all x lambda that is in the epigraph of the function f. Okay, so from here we will see that gamma has to be less than or equal to 0. Okay, let us first show that. Gamma is less than or equal to 0. How come this is true? Okay, now because this is true, whenever x lambda is in the epigraph of f, we can fix an element x that is in the domain of the function f. Then f of x plus alpha will be in the epigraph of f for all alpha greater than or equal to 0. So over here we can pick x to be x naught is fine to do so because x naught is in the domain of the function f. Okay, so if we do this and we apply this inequality, we obtain the following: the inner product of v and x plus gamma times f of x plus alpha is less than or equal to the inner product of v and x naught plus gamma times lambda naught minus epsilon, and this is true for all alpha greater than or equal to 0. Okay, what happens if gamma is strictly positive? By contradiction, suppose that gamma is positive. Okay, then we can divide both sides by gamma and get the following. Then v over gamma x plus f of x plus alpha is less than or equal to v over gamma x naught plus lambda naught minus epsilon, and this is true for all alpha greater than or equal to 0. Okay, now the right hand side here doesn't depend on alpha. Okay, so and this is true for all alpha greater than or equal to 0. Then we can let alpha approach infinity and get a contradiction because the right hand side here is just a real number and it doesn't depend on alpha. Okay, so letting alpha approach infinity gives a contradiction. Therefore, gamma has to be less than or equal to 0. From this inequality, we already showed that gamma is less than or equal to 0. And in fact, we can actually show that gamma is strictly less than 0 in the next step. So, by contradiction, suppose that gamma is equal to 0, okay? Because we already know that it's less than or equal to 0. then what happens from here? Then from here, we can apply this inequality for x equals x naught and lambda is equal to f of x naught, and get the following. Then the inner product of v and x naught plus gamma, that is 0, times lambda, that is f of x naught, is less than or equal to the inner product of v and x naught plus 0 times f of x naught minus epsilon. So from here, this is just 0, this is 0. We end up having that 0 is less than or equal to minus epsilon. That is a contradiction. Okay, so from this contradiction, we see that gamma has to be strictly less than 0. Okay. Now to finish the proof, we are going to apply this inequality again. Okay, and observe that gamma is strictly less than 0. Now, if we fix any x in the domain of the function f and let lambda be f of x, then we apply this inequality and get the inner product of v and x plus gamma times lambda, that is f of x, is strictly less than, it's less than or equal to, is also fine, the inner product of v and x naught plus gamma times lambda naught minus epsilon. Okay, and because gamma is strictly less than 0, we can divide both sides by gamma and get this v over gamma x plus f of x is less than or equal to, now we have to change to greater than or equal to because gamma is strictly less than 0. The inner product of v over gamma x naught plus lambda naught minus epsilon over gamma. Okay, by rearranging this inequality, we see that f of x is greater than or equal to v over gamma and then x naught minus x plus lambda naught minus epsilon over gamma. Okay, and now we can divide this by phi of x. Okay, then we see that phi is just an R phi function and phi of x is less than or equal to f of x for all x in Rn. So then phi of x is less than or equal to f of x for all x in Rn, where phi of x is given by this formula. So phi of x is just the inner product. We can write in this way: v over minus gamma x plus v over gamma x naught plus lambda naught minus epsilon over gamma. Over here, a is actually this is a and this is b. Okay, so phi of x has the form ax, the inner product of a and x plus b, and so it's an R phi function and it satisfies this inequality, and therefore the proof is complete.